Hello and welcome to today's presentation, a quick guide to installing linear heat detection. Thank you for taking the time out and being here today. My name is Gary Paul, and I'm the Regional Sales Manager for the U.S. and Canada here at Protectowire. I'm also a member of the National Fire Protection Association and the Society of Fire Protection Engineers. Before we begin, I have a few housekeeping items to cover in the presentation. First, today's webinar will be available on demand after the live session and will be emailed to all registered participants. Down below is a live chat feature where you can submit any questions you may have. You can also email questions to info@protectowire.com. Also, be sure to answer the polling question on the bottom of your screen before leaving and check out the additional resources under the Offer tab as well. So, without any further ado, let's get started. Let's start with a quick introduction. Protectowire linear heat detectors are a series of fixed temperature devices. Their unique design enables their use in several challenging applications where conventional detectors simply cannot reach. Except for fiber optic, Protectowire linear heat detectors are categorized as a digital device, which is simply to say the condition of the device is either on or off. The first linear heat detector was invented back in 1938 by Gerald Holmes, the founder and original owner of Protectowire, and has been listed with both UL and FM since the 1940s. Linear heat detection can be best described as a continuous chain of spot heat detectors, with the ability to sense heat or sudden increase in temperature anywhere along its length. A common misconception is linear heat detection comes only in one form. I'd like to take a quick moment to introduce the family of linear heat detection that has been developed over the years to meet a variety of challenges. To start, there is the PHSC series detector, which stands for Protectowire Heat Sensitive Cable. This is the product most widely used and the detector that most relate to when they hear the name. Comprised of two steel conductors, the PHSC series can be integrated into any conventional or addressable system. However, there are limitations when considering equipment, which we'll get into in a few moments. Next is the PLR series, which stands for Protectowire Low Resistance. Same construction as PHSC, the PLR series adds copper-coated conductors to reduce the cable's overall resistance value from 0.185 ohms per foot, which is the standard resistance value of steel, to 0.058 ohms per foot. That's roughly a 2/3 reduction in resistance value. Lower resistance equals longer runs. The most recent development in linear heat detection is CTI, which stands for Confirmed Temperature Initiation. Replacing the steel core conductors of our standard PHSC series with copper and constantan creates a Type T thermocouple, providing us the ability to measure physical temperatures at the location of the fault. Through the required CTM530 interface module, we can now program the initiation temperature and compare it to the temperature of the fault. Through this process, we can discriminate between a mechanical failure and an actual true heat event. And lastly, we have fiber optic, which is widely viewed as the next generation in linear heat detection. Standard digital linear heat detection is considered a passive device, meaning that it sits in a ready state waiting for the fixed temperature to be achieved before activating. Fiber technology, on the other hand, is an active system that reports real-time temperature profiles anywhere along its length up to 10 kilometers. That's a little over 32,000 linear feet off a single fiber, and then can be further segmented or zoned into 256 unique partitions anywhere along its length, which is all done through software. Along with a broad range of detector options, we also offer a broad range of jacketing options. The primary function of the outer jacket is to provide protection from the various environmental conditions the detector may be exposed to. Our EPC jacket, which is available in both our PHSC and CTI series, is a PVC jacketing material suitable for light industrial and indoor applications. Type XCR is our acronym for Extreme Corrosion Resistance. As the name implies, This fluoropolymer jacket is a Teflon material, well suited for extreme conditions. It offers resistance to a wide range of chemicals, solvents, and oils. It also has the ability to withstand UV rays, so it's well suited for both indoor and outdoor installations and heavy industrial applications. Type PLR is specific to our low resistance detector and is a polypropylene rubber-based jacket. It's UV stabilized, so it too is suitable for outdoor applications and also resists many of the same chemicals, oils as the XCR jacket and provides excellent flexibility in low temperatures. And finally, Type XLT is our most recent development and stands for extreme low temperature. This is our lowest rated jacket, which is rated to minus 60 degrees Fahrenheit, and is available only with our 135 degree detector. Offered both in PHSC and CTI series, this particular product was developed specifically for the industrial freezer market. Within the special hazards community, linear heat detection is a niche element, providing protection primarily in industrial settings and commonly installed to provide open area protection. Within UL and FM guidelines, it's listed in the same category as spot heat detectors with similar open area listed spacing, typically 50 feet per UL and 25 to 30 feet per FM. Given its unique construction, linear heat can also be woven in close proximity or direct contact with the item or apparatus that's being protected. This is typically referred to as proximity detection, and where linear heat really shows its versatility. This chart shows each detector's FM approved and UL listed spacing for each of the Protectowire linear heat detectors. Note that Type 356 and 500 don't have an approved spacing per FM or UL. They are listed per FM for special proximity detection applications only. Examples of this would include conveyors, fixed or floating roof tanks, kitchen hoods, things of that nature. As we discussed in the previous slide, all series of Protectowire linear heat carry some form of recognition from FM and UL, whether it's open area spacing or simply special hazard proximity detection. To further our discussion on listed spacing, it's important to understand how the spacing guidelines are applied when it comes to heat detection. The spacing rules for heat detection are defined in NFPA 72, Chapter 17. More specifically, Chapter 17.6.3 under the heading Location and Spacing. As referenced here, all listed spacing is based on a 10-foot smooth ceiling, but as we all know, that's just the tip of the iceberg. More often, we're dealing with ceiling heights ranging much higher than 10 feet and typically over 100 feet. This table shows the required reduction factor based on the physical height of the ceiling the device is going to be installed. As the ceiling height increases, the effective spacing of the detector decreases. To illustrate this, consider our 50-foot spacing per UL on our 155 detectors. The 50-foot spacing is allowable only on ceilings up to and including 10 feet. As the ceiling height increases, the derating multiplier decreases. So, to apply some simple math, at 30 feet, what was once our 50-foot spacing, now it becomes a factor of 0.34 times that listed spacing. So, 50 feet times 0.34 gives us a net figure of 17 feet for our new listed spacing figures. However, when the ceiling exceeds this 30-foot threshold, the spacing reduction formula converts from a factor of the listed spacing to a factor of the actual ceiling height. We receive a lot of questions asking if linear heat detection can be installed on ceilings 30 feet or higher, and the answer is yes. At heights above 30 feet, Chapter 17 refers us to the reduced spacing exception, stating, the minimum spacing of heat detectors shall not be required to be less than 0.4 times the ceiling height. In NFPA 72, Annex A provides explanatory material to help provide some understanding to these guidelines. Annex A, Section 17.6.3.5.3, provides the following. The width of the uniform temperature of the plume when it impinges on the ceiling is approximately 0.4 times the height above the fire. So reducing spacing below this level will not increase response time. For refrigerated storage, FM Global Property Loss Prevention Datasheet 8-29 states that the lowest temperature detector should be selected and that for other than smooth ceilings, the detector spacing should not exceed 1/2 the listed spacing, or the full allowable spacing of the sprinkler. Protectowire's PHSC 135 XLT and the newly introduced CTI 135 XLT both have the lowest activation temperature of any digital linear heat detector on the market and developed specifically for the refrigerated applications. Okay, now we're getting into general installation guidelines. These, to start, we're just talking about, basic housekeeping and some common sense areas where you can get some information to help you with the project you're working on. Of course, first and foremost, always follow applicable codes and standards within your jurisdiction. We do have some guidelines that are available to you for download. PHSC, Important Installation Information, that's on our form DS 7736. We also have one for our CTI, Important Installation Information form there. That is on form DS 9271. Both are available for download from our website. Always follow recommendations in any of the installation or maintenance manuals provided by Protectowire. For CTI, of course, we're dealing with the thermocouple principle throughout. Always follow the instructions included there. You can also get additional information through our CTM 530 interface module manual. And of course, AHJ is always going to have the final say on any application that you're working on. Always consult with your AHJ. Any questions you may have, please feel free to contact any Protectowire representatives. Pay close attention to the type of detector you're using and use only the appropriate feed cable. For PHSC and PLR series, use only approved copper feed cable with a minimum conductor size of 18 gauge. For CTI, we're dealing with the thermocouple principle, so we'll get into that in a couple of minutes, but different feed cable. Our junction boxes have been selected to meet a wide range of environmental conditions. They also come equipped with the appropriate terminal blocks to accommodate the detector being used. Again, CTI requires the Type T terminal block because of our thermocouple principle. So we've developed a specific part number to make sure that you're getting the appropriate equipment. And of course, the use of wire nuts or any other non-approved connection method would be considered improper installation techniques and could possibly avoid warranty. As we illustrated previously, unlike our Legacy Series detector with steel and copper-covered steel conductors, the use of a Type T thermocouple cable to communicate an accurate temperature profile is critically important with the CTI Series detector. It's what sets it apart. Each connection point branching from the interface module and in contact with the CTI detector must maintain this principle of dissimilar metals, and these two metals are copper and constantan. It's also crucial to view these two metals as your polarity. With steel, we can reverse polarity, so to speak, and not impact the detector's ability to initiate. However, in a CTI series system, we can only use Type TX extension grade thermocouple wire as our feed cable. With the thermocouple, if we reverse polarity, we can induce what's referred to as a parasitic junction. Instead of reporting an accurate temperature profile, you can actually see information that starts ambient and then begins to jump as heat is applied. In most cases, these numbers will decline and show negative readings. If you experience this during your commissioning or testing process, then it's almost certain that you reversed wires somewhere in your run, or you might have a terminal block that's improper. Again, we offer the appropriate junction boxes that have been selected and equipped with the proper terminals to accommodate the CTI system. And here we have a classic illustration of a Class B or Style B wiring. For all detectors, The appropriate feed cable is brought into the junction box at the start point of your zone. Feed cable is landed in the appropriate terminal block. For PHSC and PLR, it doesn't really matter which post you use since we're not really concerned about polarity. But for CTI, we must pay attention to polarity and be sure that we're actually connecting the copper conductor with the copper post in the terminal block and the constantan to the constantan post in the terminal block, which are color-coded so it's easy to identify. The detector is then run through the zone as needed and prescribed, and then landed at the end of the zone in your end-of-line box. From there, we're making the same connection points as we did in the beginning. The only difference is here we're conditioning the line with the end-of-line resistor. Where linear heat is classified as a non-restorable fixed temperature device, the only testing required is to short the detector at the end-of-line resistor. Inducing an alarm or a fault condition from this point confirms the detector is intact and communicating properly with the panel. And similar to our Class B, here we're showing the installation using Class A or Style D wiring. As you'll notice, the illustration is very similar to our Class B wiring diagram. Primary exception is rather than ending with the end-of-line resistor, we're continuing the circuit, and the end of the zone is transitioning back to the appropriate feed cable, which is then routed back to the control panel or interface module. When it comes to the physical location of the detector, the space it occupies and the area it will be installed will dictate where it can be positioned. From there, we follow the guidelines we're going to cover based on the shape, style, and as we discussed before, the height of the ceiling. Heat from a fire rises to the ceiling in a plume and spreads radially from the fire source. As the hot gas is cooled, they begin to bank down from the ceiling. The corner, where the ceiling and the wall meet, forms an area known as the dead air space, as shown here. This dead air space is the triangular area formed along the ceiling by measuring 4 inches or 10 centimeters out from the corner and 4 inches, again 10 centimeters down the sidewall. Protectowire should not be placed in this area. On smooth ceilings, interrupted by projections no more than 4 inches lower than the ceiling, the distance between parallel detector runs shall not exceed the maximum listed spacing. Also, detector run is required to be within a distance of 1/2 the listed spacing when measured at right angles from all walls or partitions, which extend to within 18 inches or 46 centimeters of the ceiling, as shown in this illustration. With solid open joists, greater than 4 inches from the ceiling and less than 3-foot spacing, or other similar structures, heat travels freely down the joist channels. However, heat has trouble spreading across the joists, so the distance in this direction must be reduced. The protectowire shall be mounted on the bottom of the joist, and the spacing of the detectors on all runs parallel to the joist shall not exceed 50% of the smooth ceiling spacing. In the case of beam construction, where the beams are 4 inches, 100 millimeters, or less in depth, the ceiling shall be treated as the same as the smooth ceiling. If the beams project more than 4 inches, more than 100 millimeters, below the ceiling at right angles to the direction of the beam travel shall not exceed 2/3 of the smooth ceiling spacing. In the case when solid beams are spaced greater than 8 feet, or roughly 2.5 meters on center, and the beams project greater than 18 inches or 46 centimeters below the ceiling, each bay formed by the beam shall then be treated as a separate area. In a shed slope ceiling, a row of detector is required within 3 feet of the high side of the ceiling. Spacing will then follow the requirements for spacing of that ceiling type that you encounter. Spacing is to be based on the horizontal projection of that ceiling. In a peak slope ceiling, similar to a shed ceiling, a row of detectors is required within 3 feet of the high side of the ceiling. Spacing then will follow the requirements for spacing of that ceiling type. Spacing shall be based on the horizontal projection of the ceiling, and ceilings with less than 30 degrees slope use ceiling height of peak for spacing. Greater than 30-degree slope, use the average slope height, except for those at peak. When choosing a detector, the first step is to choose the lowest alarm temperature rating, which has an ambient temperature appropriate for the application. Then, choose a jacket type most suitable for the environment. Consider both physical and chemical conditions it will be exposed to. It's also important to consider what listings or approvals may be required. Not all detectors have both FM and UL ratings. And lastly, CTI should be considered for all applications where false alarm discrimination is crucial. And next we get into the features and benefits of working with Protectowire Linear Heat Detection. First and foremost, it's a simple and reliable open switch device. Its unique construction allows it to be installed in a variety of different locations, giving it superior coverage of both protected areas as well as being able to be installed in close proximity to the hazard. It's very easy to install. It's very easy to service. It's very easy to test. Service life is always a common question we receive, and our answer is always, it depends. Where and how it's installed, along with the environments it's installed in, will all impact the detector's useful life. Each lot of linear heat detection goes through a rigorous quality process to assure the highest quality standards are maintained. The Protectowire company offers an assortment of approved fasteners and splicing devices to facilitate installation for both standard and special applications. Approved fasteners are generally designed to lightly clamp the detector, which enables the tension to be applied progressively. This method is better than arrangements which apply a high tensile load at the end of each run or clamp and compress the sensor cable so tightly that the inner insulation becomes damaged. To ensure a trouble-free installation, only factory-approved fasteners should be used. The use of non-approved fasteners may physically damage the detector, thereby causing false alarms, and in some cases, void the detector's warranty. Shown here are some common examples of accessories used when mounted to cable trays. Each clip is designed or chosen to accommodate different material thickness and a wide range of applications, such as cable trays or storage racks, and even sailing joists. And here we see a great example of one of our spring clips being used on a steel beam. As you can see, we're just gently supporting the detector. Conveyors are a common application. Some of the issues we see in these areas include bearing failures and belt slippage, both of which could cause overheating and potential fire. With its unique construction, linear heat can be used to provide proximity detection to these areas to detect and react as quickly as possible. In some cases, the conveyors are covered with metal hoods. In these areas, we can provide detection not only below in the area of the bearings and belts, but also above the materials being moved. In these areas, however, access to connection points to support the linear heat are limited. To accommodate long spans like this, you have the option of having the linear heat detector coupled with a messenger wire. As shown here, messenger wire is available with any model detector on special order. It consists of high tensile strength stainless steel wire which is wound around the detector at the rate of approximately 1 turn per foot, or every 0.3 meters. It's a carrier or support wire which is designed to simplify the installation of the detector in areas where mounting is difficult due to either lack of appropriate support structures or mounting surfaces. When using messenger wire, turnbuckles and eye bolts must be employed at each end of a straight run to apply the appropriate amount of tension to support the detector over these long spans. The maximum length between turnbuckles should not exceed 250 feet or 76 meters. And the wire must also be supported with the approved intermediate fasteners at intervals typically ranging anywhere from 15 to 20 feet or 4.5 to 6 meters. The final spacing of intermediate fasteners is largely determined by the individual application. However, Spacing should never exceed 50 feet or 15 meters, as you may experience some excessive sag. Outdoor, messenger wire installations present an additional challenge due to environmental factors such as snow and ice buildup or wind. Increased detector support must be provided by using additional supports with closer spacing. And here's a great illustration of the components required and the method used to properly install your messenger detector. A copy of these guidelines is available through our website. One of the most popular applications for linear heat are warehouse storage and industrial freezers. In these facilities, linear heat is typically a component of the pre-action system. In freezers, it's the primary releasing mechanism for filling a dry pipe system. When installing for in-rack detection, the detector should be positioned in the flue space at the same level or alternating levels with the sprinkler pipe. Typically, it would be recommended that the detector be fixed directly to the sprinkler if possible and permitted in your jurisdiction. It's still acting as an integral part of the releasing system. However, in a manually operated and active storage facility, the in-rack sprinklers take an incredible amount of abuse. This is the one area we recommend keeping the detector off the sprinkler pipe and as far out of harm's way as possible. With this level of exposure, it's not a matter of if, but when the detector will be compromised. Again, as a digital contact device, the PHSC series does not have the ability to distinguish between heat and physical damage, which is why CTI should be considered in these applications. Providing the ability to know the temperature at the spot of the fault will avoid costly false alarms. Of course, this is specific to in-rack detection. At the ceiling level, the opportunity for damage is greatly reduced. In this area, it would be advisable to follow the sprinkler pipes and attach directly if at all possible and permitted. To do so, we recommend double loop pipe straps. This provides your installers the ability to cinch the cable tie to the pipe securely without compromising the detector. The first loop serves as your anchor, whereas the second loop provides a taut but loose support of the detector to avoid any damage. For in-rack, we have a variety of clips available to accommodate the installation, including our WAW, OHS clips, and our newly introduced JD1 clip. The JD1 clip was developed to provide installers an easier method of supporting and installing linear heat detection. Most, if not all, the supports offered are closed-loop format. These have been effective accessories for a great many years, but are sometimes problematic when making quick repairs. To do so would typically require the removal of the clip, and then the detector, and then reinstalling the clip along with the detector. A lot of time and effort is spent in between. The JD1 design resembles a J slot with an open top and a slightly narrowed opening. The open top allows for a quick installation and removal of the detector without the need to remove or replace the clip, saving you both time and money. It's possible to install pull stations in line with standard linear heat. However, due to its spring steel construction, Protectowire cannot be bent less than its allowable 2.5-inch bend radius without potential damage. Our PFL flexible leads allow the termination of Protectowire in these tight spaces without compromising the detector. As I mentioned earlier, we offer a variety of standard junction boxes specific to the type of detector you're working with and the location of your application. For light industrial indoor applications, our ZB4 is NEMA 4, 4X, and 6P rated and suitable for a broad range of indoor applications. For outdoor and harsh environments, we have the ZB-HD series, which is fiberglass reinforced and suitable for a broad range of indoor and outdoor applications. And here we see the junction boxes specific to our CTI detector. The only difference between these and what we saw in the previous slide is that terminal block that you see in front of the screen. That terminal block is specific to CTI detectors only, providing us the continuation of that thermocouple principle throughout the run. Strain relief connectors are required to make the penetration into the zone box. The Model SR502 strain relief was selected to securely hold the cable in place while maintaining the appropriate NEMA ratings. These strain reliefs are available in both nylon and galvanized steel. Another convenient aspect of linear heat is your ability to make repairs to the detector. This is accomplished first by identifying the location of the fault. Depending on the facility and the application, there could very well be more than one fault location. Once these areas are located, you can follow these instructions to properly remove and splice in the new section of detector. For PHSC and PLR series, we follow the steps illustrated here. Since we're working with steel conductors, the use of our PWSC splice connector is required. A copy of these instructions are also available on our website. In addition to the PWSC splice connector, we also offer our PWSK splice connector. This is the threaded assembly providing a watertight and oil-tight seal that grip the Protectowire Linear Heat Detector securely. This kit provides a simple method of making inline splices while allowing easy disassembly for service and proper environmental protection without the use of a zone box. Like the PWSC connector, this splice connector is specific to our PHSC and PLR series detectors. When it comes to our CTI series, we must maintain and accommodate the dissimilar metals of copper and constantan when making splices. The CTIC splice connector is comprised of our dissimilar metals and provides the only acceptable means of repairing a fault within the CTI system. Aligning the appropriate conductors is crucial in maintaining the ability to accurately report temperature conditions when the detector is in a fault or alarm state. Another benefit of working with standard digital linear heat is the fact that all our PHSC series detectors are electrically compatible. What this means is that it's possible to combine different temperature models on the same initiating device circuit. Since activation is predicated on the melting of the heat-sensitive polymers and exposing the conductors, we're only concerned about an on or off state. Combining varying initiation temperatures enables you to accommodate any fluctuations in ambient conditions you may be faced with without the need to zone a higher or lower initiation temperature separately. Again, this is specific to PHSC series only, as CTI requires the use of our CTM530 interface module to provide the false alarm discrimination. It's not possible to combine different temperature detectors along the same IDC. Due to the thermal coefficient of the expansion of steel, Protectowire linear heat detectors will expand and contract in length with changes in temperature. In applications where extreme temperature changes are expected, it's important to leave adequate slack in the conductor. This assures contraction of the detector will not put stress on mounting hardware or the detector itself. The table above shows the recommended slack or sag that should be introduced when installation occurs at an ambient temperature of 70 degrees. When it comes to storing your linear heat detector, there are a few areas we want to avoid to assure the integrity of your device. First, do not store the detector in any areas that may exceed the detector's max ambient temperature. Each of the detectors have a specific fixed temperature rating. Along with its activation temperature, we also have a max ambient condition these can be exposed to due to the composition and physical melt temperatures of these heat-sensitive polymers. You want to be assured to avoid storing the detector in your vehicle or trailers in hot, sunny areas. Next, like the exposure in a hot vehicle, we want to avoid storing the detector near any heat sources, such as boilers or furnaces. Every lot of linear heat is tested before it leaves our facility. However, during the summer months, it's possible to expose the detector to heat while in transit. We provide instructions with every shipment on the proper techniques to test the detector upon arrival. Like our guidelines for storage of your device, we also have a few areas to pay close attention to while installing your detector. First, You want to avoid any mechanical stress of the detector. The support should not pinch or crush. Be sure to use only Protectowire-proof fasteners. Do not make or induce any 90-degree bends when installing. All bends should be made by hand and not exceed the minimum 2.5 bend radius. Do not paint the detector. Doing so will void your listing. Allow for the appropriate expansion or contraction that may occur as a result of the temperature of your facility in the area you're protecting. This refers back to the thermal coefficient of steel we discussed earlier. And lastly, make sure all terminals and splices are compatible with the detector series that you're working with. This last note refers specifically to CTI. Testing of linear heat detection is established through NFPA 72, Section 14, under test methods for initiating devices, more specifically, heat detectors. Under Table 14.4.3.2, NFPA identifies heat detectors in two classes. The first being a fixed temperature restorable or spot type heat detector, and the second being a fixed temperature non-restorable or line type heat detector. Protectowire is identified as a non-restorable line type heat detector, and as such, NFPA guidelines does not require a heat test be performed, as it would damage the non-restorable device and require immediate service. Rather, it requires a functionality test be performed. Electrically, all that's required is the detector is shorted at the end of line zone box. The ability to induce an alarm or a fault condition from this point verifies the integrity of the detector. Considering the testing requirements of line type heat detection versus spot type heat detection, you can quickly see the advantages of working with linear heat. In this slide, we're looking at an aircraft hangar with approximately 6,000 linear feet of linear heat broken down into 3 zones. Protection is provided up in the ceiling area of the facility, with the appropriate zone boxes installed at the beginning and end of each zone. We're then able to transition back out of the zone with the appropriate feed cable to locate the end-of-line junction box in a convenient location. Here we see the junction box is located a couple feet above the exit. In this example, testing of the 3 zones is done from this one location by simply shorting the detector. The use of a restorable, fixed temperature device, like a spot heat detector, would require each detector be tested with a heat source individually per NFPA guidelines. This would require a scissor lift, removal of any aircraft, and a few days' time. Considering linear heat in areas and applications like this will ultimately save you time, money on both your installation and annual testing. As we illustrated in the previous slide, the test procedure may be easily accomplished in a Class B initiating circuit by using the built-in test button contained in some factory-supplied end-of-line zone boxes, or by using a jumper wire to apply a short across the end-of-line resistor to create an alarm. In a Class A initiating circuit, the recommended procedure is to remove the plus and minus return legs of the circuit at the control panel terminals. This action should cause a trouble signal at the control panel. To create an alarm condition on the circuit, as alarm overrides trouble, place a jumper across the disconnected return leads. This action will cause a necessary alarm condition to activate the circuits and complete the test. When measuring the loop resistance, place each circuit in alarm and leave the short across the detection as described above. Disconnect each detection circuit wires from the terminals of the control panel. Place an ohm meter across the disconnected zone wires, out positive and out negative, and record the resistance measured. Compare these values at each annual testing. Any change in loop resistance should be investigated for possible deterioration of the interconductors, with particular attention given to termination points, inline splices, or areas of the detector where the outer jacket has been compromised or damaged. Along with the array of installation accessories available, we also provide a number of tools to aid in the testing and servicing of your linear heat installation. Testing of the CTI detector follow many of the same guidelines for Class A and Class B circuit monitoring. However, with CTI detectors, we're able to take the test procedure one step further and actually perform a heat test without damaging the detector. This is accomplished through the use of the required test probe. Rather than a test button in the junction box, the required Type T terminal blocks have a special receptacle built into them to allow the temperature probe to be plugged in directly. By inserting the temperature probe into the system will then automatically detect a fault condition. The CTM 530 interface module will register this change in status, identify the spot of the fault in linear feet, and provide the temperature profile at the location of the fault. From there, we can now apply heat from an appropriate heat source directly to the probe. Maintain the application of heat until the programmed initiation temperature is achieved and alarm condition is registered. I want to thank you all again for taking time to join us today. Hopefully the information provided was informative and brings about a lot of questions. As a quick reminder, any questions you may have can be emailed to us at info@protectowire.com. Also, don't forget to submit your vote on our polling question and check out the offers provided under the Offer tab. Again, my name is Gary Paul, and it's been my pleasure to speak with you today.